Hi, I'm Hui-Ping. So I'm the PhD student in Electrical and Computer Engineering department. Yeah, so today I'm going to introduce magnetic semiconductor, including intrinsic magnetic semiconductor, diluted magnetic semiconductors, yeah, and some ferromagnetic dope to the materials. Yeah. So first I want to introduce the properties of the magnetic semiconductor. So we can see for the energy Venn diagram for non-magnetic semiconductors, their energy Venn diagram is symmetric. But for the magnetic one, it is asymmetric. And this property enables us to use gate voltage to control the Fermi level and then get spin polarized current. So you can see the Fermi level here only across the area of the spin up electron. So since it enables spin polarized current, then it is useful in spintronic device or magnetoresistive device. Yeah, but however, so for intrinsic magnetic semiconductor, so this paper is in 1960s. Yeah, so the iridium oxide and iridium sulfide are some of the most earliest founded intrinsic magnetic semiconductor. However, they obtain very, very low Curie temperature, and also they contain rare earth atoms. So it is not very good for device application. Yeah, so that's why researchers started interested in diluted magnetic semiconductors. And the other reason researchers interested in DMS is because the technology of molecular beam epitaxy has been developed in 1990s. Yeah, so then researchers are able to synthesis compound semiconductor doped with manganese ions. Yeah, so this is the Indian manganese arsenide researchers synthesis. Yeah, it's about 1% manganese dopant. Yeah, so scientists measure the Hall resistivity versus the resistivity and make this plot. And they also measured the remnant magnetization and make the second plot. Yeah, so they found that these two plots has a proportional relation. Yeah, and it shows that the very first DMS have obtained a Curie temperature around 7.5 K, also very low. Yeah, but later more people interested in the field of DMS, and they want to see if we have higher manganese dopant concentration in the compound semiconductor, how would the Curie temperature goes? Yeah, so it contains two parts of their simulation. So the first part is the relation of the Hall concentration and the Curie temperature, and their conclusion is higher Hall concentration will cause high Curie temperature. Yeah, and the second part, they consider the dopant concentration. Yeah, so overall we can see Curie temperature could be enhanced, could be increased by highly doping and high Hall concentrations. Yeah, so they got this final estimation plot for several kinds of compound semiconductors, and we can see for gallium nitride and for zinc oxide, in theory, they could achieve room temperature, Curie temperature. Yeah, and so for the right part are the experimental research of manganese doped zinc oxide. So they indeed achieve room temperature at ferromagnetism, and even under 500 Celsius degrees to 900 Celsius degrees. So the ferromagnetism still exists. So this is the history of the diluted magnetic semiconductors. Yeah, and then we goes to the topic of 2D material. So transition metal dichalcogenides is a kind of 2D semiconductors which have been developed since 2011. Yeah, and so MOS2 and WS2 are the two most studied TMD semiconductor, and they can very easily fabricated, easily synthesize this by chemical vapor deposition, and you can obtain a very large area of this 2D film. Yeah, but also we look at intrinsic 2D ferromagnetic materials first. Yeah, so although magnetic semiconductor researchers are very interested on them, however, for 2D ferromagnetic materials, they also obtain very low temperature for the intrinsic ones. Yeah, and so in this chart, only VSE2 obtain obtain current temperature higher than room temperature. Yeah, but it's not too high. Yeah, so not good for application. Yeah, so so then people think of the concept of DMS, and then they want to try if we can dope ferromagnetic atoms into MOS2. Yeah, so this is one of the experimental research. So they use hydrothermal synthesis to generate MOS2 nanostructures. Yeah, and they use 3 kinds of precursors, and then they have these materials. So this is a TEM picture, and you can see the layer structure in the TEM pictures. And they also measure the image curve, yeah, and then found it obtained ferromagnetism in 100K, but still not above Curie temperature. Yeah, so but people still don't give up on this topic, so they have some simulation research to estimate the theoretical TC of manganese doped MOS2. Yeah, so how to do the simulation? So they considered different kinds of defect sites, like manganese in sulfur site or molybdenum site. And they also consider the clusters case, which is these two. Yeah, because they say they mentioned that in reality, so doped MOS2, the dopant sometimes not distributed very uniformly. It will have clusters on your 2D films. Yeah, so in this case, though, the concentration is 1.85%. Yeah, and they use hybrid density functional theory and mean field approximation for TC calculation. Yeah, so this is the projected density of states of different cases of defect sites. Yeah, so so we can see for the for figure D, you can see that for the y-axis it means density of states for spin up electron or spin down electrons. Yeah, so we can see for figure D, in spin up electron area, there are some density of states distributed here, but no density of state distributed in the downspin side. So this could call a semi-metal, like only spin up electron could pass through this material. Yeah, and so this figure A actually the same as this one, but it has a larger Y scale. Yeah, and this figure compares single molybdenum defect and cluster defects, and they found they generate different magnetic moments. Yeah, and they also have the Curie temperature estimation, and they found for different kind of carrier doping. Sometimes for whole doping, it always shows ferromagnetism, but for electron doping, in some concentration, it will appear anti-ferromagnetic doping. Yeah, so, and one note for this literature is it mentions that although clustering of defects can preserve magnetic moments, but their easy access may be different from single magnetic defect due to lower magnetic and isotropic energy. Yeah, so I think their conclusion is, so these are all theoretical simulations. Yeah, and if your doping in reality, it is very not uniform, then the resulted magnetic moments will be even complicated.
Give it 1 more minute.
Okay, so the last work I want to show is a vacancy doped MOS2. So it actually doesn't contain any ferromagnetic atoms, but it has different phases of MOS2 contents in the whole film, and they also they observe room temperature ferromagnetism in this kind of material. Yeah, and this is their calculation of the density of state. Yeah, and those are the challenges for development application of magnetic semiconductors. Yeah, including low Curie temperature and high concentration doping will causes interstitials in the semiconductors and reduce the effective magnetic density. Yeah, and it is difficult to obtain monolayer plus larger ferromagnetic doped to the material so far. So